Okay, so I think I will start so we don't delay too much, access to the beach. So remember I was going yesterday over the procedure for constructing the co-splicing network. So you have, for a gene, you have exons. Two samples have different exon counts. You compute the Canberra distance or the cosine for each gene separately. Now you have n genes, and each one has a matrix. You compute the Mantel correlation between all pairwise distance matrices, and then this is your adjacency matrix. And from there on, everything is WGCNA. Nothing else changes. So how do you do this in R? So first thing is, how do you represent the data? So the way I like it is you have for each, you have gene 1, exon 1, gene 2, exon 2, and so on for each gene. So each row is an exon expression level, and these are the samples. And you construct kind of a list or a vector, character vector, and it just says gene 1, gene 2, or for each of these rows. So it has to correspond to the rows over there. And yes, friendly advice. I come from MATLAB. So then when I come to R, I find that almost every single coding mistake I make is because I don't understand the data representation in R to this day. So what I do, I just make sure everything is either a matrix or some character vector or so on. That's my approach. And I don't want to understand tables and nested lists and all that fun stuff. So what do you need to do co-splicing network analysis? So you need a multi-core desktop computer, a reasonable amount of RAM. So I have 12 gigs, and I have like a quad core, or something like that. So that's fine. You need the for each package and a cup of coffee. So let's go over the for each package. So all of these matrix correlations will cost you time. So you have processors, and you want to use them. And you want this process to be as painless as possible. So the for each package is such a tool. Imagine you have a loop, and it takes forever. So you want to farm each iteration of the loop to a different processor. Okay, so that's the extent of my parallel programming skill set. So the main reason for using this again is that it supports parallel execution. Instead of you having a for loop, you have a for each loop. That's all there is to it. And there's also the mapply function. So imagine that you have a vector or like a list, and you want to do the same operation on each element of this list. So this is the function that I use. And so the input to this is like a list of different arguments. And then the second, more arguments, is if you want to apply, like let's say you have a list of vector and it's some numbers there, and you want to add 1 to each one of those. So more arguments would just be 1 then, and your function would be plus. So I apologize for those of you that are experienced programmers. So I assume here that you haven't seen R before or something like that.
Yeah, that's a good assumption.
Okay. So here's the code for the co-splicing network. So the first step, you load your data. You make sure that it's in the format that I just described. You have your number of genes and your gene names and so on. So now we have the for each loop. So I go and I select for each gene all its exons. So let's go back to the data. So the first iteration of the loop, you go and you say, oh, what says gene 1? So you see the first 3 rows are all gene 1, and those are the exons. So now you select that matrix out of your whole data set. So that's what that does. So now you look, if it's just one axon, you have to transpose the data. But basically, you just compute the distance between the samples. And this is the code for that. It's very simple. So now you have, where are we now? We computed all these distances. We computed all these guys after we went through the for each loop. So now we have all these matrices. And how did that happen? So I use the for each. So the parameter here for each is dot in order. In this particular case, you set it to true. So because sometimes one processor will finish before the other, and it's not the same order that it's in your original list. Let's say that you do some kind of bootstrapping, and then you don't care. So whenever if you randomize the data and you want some results on random data, you don't care if the first random set comes before it should be. So then you put in order false, and you have some increase in speed there. Okay, so far so good. We have already, for all the genes, we have the distance matrices. So now we have to go to another loop, and here we have the mapply function. So the output from this is a list, and in each list is one of these matrices. So now, what is the representation for all this object? You have a long list, and in each list is a matrix. And that's my first input to the mapply function. So now each processor will take one of these loops. So the first processor goes and says, OK, I got your list of matrices. And if you're the first processor, you're going to get the first distance measure. If you're the second processor, you're getting the second distance measure, and so on. So what do I apply? What's the function that I apply? I apply the correlation. And in this case, I use the Pearson. So each processor will get all the data, and either the first, the second, or the nth matrix. So when you're done, then you just have to format these results. You have to put it in the form of an adjacency matrix. So now this is your adjacency, co-splice X adjacency. If you want the co-splicing, then you just have to use the cosine distance measure over there. Okay, so that's all there is to it. So another thing, when you go and then you use the subsequent WGCNA functions, in most of them, there's a setting that says, are you expression data? And if you say false, then it assumes that it's an adjacency matrix. Okay, so that's all there is to co-splicing network construction. So now I will go a little bit into the forward selection procedure. So remember, we have our splicing distances, and they are different. We correlate each gene with a phenotype and order them in order, in a decreasing order, and so on. How does this happen in the code? So first, I go and compute my phenotype distance. So for some reason, this is cut off at the top. But the idea is you go and you have like a matrix with all your measurements. And sometimes they can be complex. So imagine that you measured several phenotypes, like we do several behavioral measures. So you can choose. You can say, OK, I'm just interested in one of the measurements. I'm interested in two in combination, or I'm interested in evaluating all the possible phenotypes together. And now you have your phenotype distance measure. Now you compute as before. We compute the distances in terms of expression or splicing. And we go on and we say, OK, rank them for me. And if you want to look which one is the top, then you just print it out. And now you construct the cumulative correlations. So remember, we take the first matrix, and that's the most significant. Then we find the second, rank 2, and we add it. And that's where I store all of that. And then I use the vegan, Mantel, you correlate the phenotype distances with the current gene distance, and then you add it to the cumulative correlations.
So there's this Mantel command.
Uh-huh.
So could you review again what's the Mantel correlation?
Yes. So let's go back to my.
I thought it's just the Pearson correlation of the distances.
Yes.
That's all it is, right?
Yes, that's all there is, and I have a slide for it from the other day. So let's see.
So I guess I'm just asking, so the Mantel command in essence just vectorizes the distance measure, right?
And computes the correlation. Yes, that's all there.
Yeah.
Oh yeah, here it is. So I think it's good to review this. So I have my genetic differences matrix, and it's symmetric, and I vectorize it. So that means I take all the unique distances. I'm not interested in the diagonal because it should be 1 or 0. And then I put this in a vector. If I have another matrix, then I do the same thing, and I correlate the vectorized distance matrices, and that's the Mantel correlation.
But I mean, if there is very little information in the original distance matrix, that is all diagonal, or 1, the others are 0. By this matrix, you have a very small Mantel distance.
Yes.
But in both cases, really not much information.
If there's no information.
But then you say that's
I don't think this would give you correlation if there's no information there. So yours.
Mantel correlation, there will be that two gene will have very high similarity.
So you're saying that if the distances are all the same.
Yeah. That you have two diagonal distances, but then the Mantel distance is small.
So that's similar to the case where you don't have variability in. So two genes have exactly the same constant expression level, right? So either there is variability in the data or there isn't.
So in Mantel correlation, the significance calculation is also in a similar way as a normal correlation?
No. So this one, this is not independent because obviously these entries are dependent. So it's permutation testing. If you want to find the p-value for whatever Mantel correlation coefficient you find, you have to give it the number of whatever permutations. That's.
You need to permute each of these, and there is no asymptotic definition.
There's no asymptotic definition, no. Steve has mentioned that there is bicorrelation formula that is more robust. And right now, I can't think of any reason why we can't use that particular correlation instead of the Pearson. But there might be one. I'm just not sure. So this is pretty much all I have.
Great. Yeah. Any other questions? Thank you very much.
Thank you.